Hi everyone, my name is Giovanni Clark. Today I'll be analyzing the spectral data for compound Y with the molecular formula C10H14O. We'll use the IR, spectra, 13C NMR, and 1H NMR data along with the molecular formula to identify the structure and interpret the chemical environment of each signal. By the end, we'll not only know what this molecule is, but why every peak fits together perfectly. First, let's start with the molecular formula, C10H14O. The degree of unsaturation, DU, also called the hydrogen deficiency index, HDI, tells us how many rings and pi bonds are present in the molecule. The formula is du equals 2n or c plus 2 minus h divided by 2. In this case, it is 2 times 10 plus 2 minus 14 divided by 2, which equals 22 minus 14 divided by 2, resulting in 4. So we have 4 degrees of unsaturation. A benzene ring accounts for exactly 4. 1 ring plus 3 pi bonds, so this immediately suggests an aromatic system. Next, we'll take a look at the IR spectrum and their key absorptions. The key absorptions present in our IR spectrum include 3050 inverse centimeters, which are representative of sp2 carbon-hydrogen stretches and can be seen as aromatic hydrogens. You also have sp3 carbon-hydrogen stretch present from 3000 to 2800, also representative of this aromatic system, and a carbon-carbon double bond stretch from 1600 to 1500, also indicative of this aromatic system. From 1250 to 1020, you have your carbon-oxygen single bond stretch, which is representative of our aryl ether or methoxy group. There are no sharp peaks that appear at 1700, so there's no carbonyl group. Using IR alone, we have evidence of an aromatic ether, not an alcohol or a carbonyl group. Next, the 13C NMR shows 7 distinct signals which already hint at symmetry. These include 158 ppm aromatic carbon-oxygen single bond, which is ipso, or the same as the carbon bonded to methoxy. 141 ppm aromatic carbon-carbon single bond, which are quaternary. 128 ppm aromatic carbon-hydrogen bonds, and 112 ppm aromatic carbon-hydrogen bond. We also have 56 ppm, which is representative of our methoxy group, 32 ppm, which is representative of our hydrocarbon that is bonded to our isopropyl, and 22 ppm, which is representative of our 2 methyl groups of the isopropyl. We have 7 carbons in total, but 10 in the formula. That symmetry suggests that it is a para-disubstituted benzene ring, or that there's para-disubstitution on several points of that benzene ring. Now let's interpret the 1H NMR. Present in the 1H NMR are aromatic hydrogens that are adjacent to methoxy at 7.35 to 7.4 ppm with an integration of 2H, or 2 hydrogens, with a multiplicity of a doublet, suggesting that there's one other hydrogen present. We have 6.9 to 6.99 with a integration of 2H, multiplicity as a doublet, which is another aromatic hydrogen, except this one is adjacent to the isopropyl. We have 3.8 ppm with an integration of 3H, representative of a singlet multiplicity. This is tied to the aromatic of the methoxy group. This is actually the hydrogens of that methoxy group. We have 2.8 to 2.95 ppm, which has an integration of 1H, a multiplicity as a septet, but a bit unclear, which is representative of the hydrocarbon that is between the isopropyl group, that is tied to that isopropyl group. In addition, we have 1.25 ppm with an integration of 6H, multiplicity as a doublet, suggesting one other neighbor. And these are representative of the 2 methyl groups of the isopropyl. So the 2 aromatic doublets, each 2H, confirm a para-disubstituted benzene ring. The methoxy singlet at 3.8 matches an aryl ether or a methoxy group. The septet and doublet combination 1H and 6H are unmistakably representative of an isopropyl group. To summarize or assemble the pieces of this molecular mystery, the molecular formula was C10H14O. We had 4 degrees of unsaturation, which represents an aromatic ring or confirms this. Our IR was indicative of aromatic carbon hydrogens and our aryl ether carbon oxygen stretch. Our 13C NMR and our 1H NMR represented our para-disubstituted ring with methoxy and isopropyl groups opposite each other. And the only structure that was consistent with all of this data is 4-isopropyl anisole. So it's a benzene ring with a methoxy group on one side and an isopropyl group directly opposite, which create perfect symmetry. Every signal here served as a clue, and when they lined up, we've solved the perfect molecular mystery. Thank you for attending.